In this video, we'll learn how to find whether two given lines are perpendicular or parallel. So let's figure this out. If two lines are perpendicular, this means the angle between them is 90 degrees, which means cos of theta, cos of that angle is 0. So if we can figure out when is cos theta 0, then we can say that in that scenario, the lines are perpendicular. Similarly, if sin theta is 0, then that means that the lines are parallel. So the lines are parallel when sin theta is 0, the angle between them is 0, and lines are perpendicular when the angle between them is 90 or cos theta is 0. Now how do we figure out cos theta and sin theta? How do we figure out when these two things are 0? So we can use the formula that we proved in the previous video. Cos of theta equals to mod of a1 a2 plus b1 b2 plus c1 c2 divided by root a1 square plus b1 square plus c1 square times root a2 square plus b2 square plus c2 square. And what are these values? a1 b1 c1 are direction ratios of line 1 and a2 b2 c2 are direction ratios of line 2. But we don't need to find this entire thing. We don't need to solve for cos of theta. All we care about is a situation where cos theta is equal to 0. So let's try making this equal to 0. When is cos theta equal to 0? So that's 0 when the numerator is 0. So just picking the numerator will work for us. Cos theta is 0 when a1 a2 plus b1 b2 plus c1 c2 that's equal to 0. So instead of finding all of these things, we can just find a1 a2 plus b1 b2 plus c1 c2. If that's 0, this means cos theta is 0. This means the lines are perpendicular. So this gives us a condition. If we can check for this condition, and if this is true, this means our lines are perpendicular. Now our job is to figure out a similar condition for parallel lines. And that's going to take us a little bit of manipulation. We'll move from cos theta to sin theta, and then we'll equate sin theta equal to 0. If you want to give this a shot, pause the video, try this yourself. Okay, let's do this. So if cos theta is this, we can figure out sin theta using this identity. Sin square theta is 1 minus cos square theta. So let's square all of this up. So this is 1 minus numerator squared divided by denominator squared. So the roots go away. Let's take the LCM. Sin square theta equals to the denominator. Here comes the denominator. 1 is replaced by a1 square plus b1 square plus c1 square times a2 square plus b2 square plus c2 square minus the numerator squared. That's a1 a2 plus b1 b2 plus c1 c2 squared. Now we don't need to solve for this entire thing. All we care about is when sin theta is 0. So we'll only look at the numerator. Yes, we'll expand the numerator. So numerator equals to, so if you multiply these two, you'll get 3 times 3, 9 terms. So here are these 9 terms. Minus, if you expand this square, you'll get 6 terms. This is x plus y plus z squared. So you'll get 6 terms. So this is x square plus y square plus z square plus 2xy plus 2yz plus 2zx. And this one we'll just expand using distributive property. Now we have 9 terms minus these 6 terms. Some of them will cancel out. Let's see. We have a1 square times a2 square. So a1 square a2 square. We also have a1 square a2 square from this. So these two will cancel out. Similarly, b1 square b2 square. Where is it? b1 square b2 square. This cancels out with b1 square b2 square. And c1 square c2 square cancels out with c1 square c2 square. So 3 terms cancel out. We're left with 6 here minus 3 here. So this is the numerator. We have a1 square b2 square plus b1 square a2 square. There's a pattern here. Plus a1 square c2 square plus c1 square a2 square plus b1 square c2 square plus c1 square b2 square. So here we have a's and b's, a's and c's, b's and c's. Minus 2 a's and b's, 2 b's and c's, and 2 c's and a's. Can you think of something that helps us group these terms? Yep, we can use the identity x square plus y square minus 2xy. So if this is our first term, this is our second term. So square of this plus square of this minus 2 times product of these two. This will be x minus y squared. So this becomes a1 b2 minus a2 b1 whole squared. Similarly, we have b1 c2 minus b2 c1 squared plus c1 a2 minus c2 a1 squared. Now we are talking. We have squares of 3 things and we're adding all of them up. When is this equal to 0? So the question is, when is the numerator equal to 0? Pause the video, think about it. So whenever we have squares added, they're almost always positive because squares are always greater than or equal to 0. So this thing is always greater than or equal to 0. This will also be greater than or equal to 0. And this will also be greater than or equal to 0. But we are given that all three of them add up to exactly 0. This can only happen when these three individually are equal to 0. So this is equal to 0, this is equal to 0, and this is equal to 0. So we have a1 b2 minus a2 b1 equals to b1 c2 minus b2 c1 equals to c1 a2 minus c2 a1 equals to 0. All three of them are independently 0. So we have three equations here. This equal to 0, this equal to 0, and this equal to 0. Let's see what we have. If this is 0, we have a1 b2 equals to a2 b1. If this is 0, we have b1 c2 equals to b2 c1. And if this is 0, we have c1 a2 equals to c2 a1. We can rearrange these. We can see that this makes a1 by a2 equals to b1 by b2. This makes b1 by b2 equals to c1 by c2. And this makes c1 by c2 equals to a1 by a2. And if you look at these three, we have a1 by a2 equals to b1 by b2, which is equal to c1 by c2. So all three are in fact equal. After all the hard work, what we end up with is this condition. a1 by a2 equals to b1 by b2 equals to c1 by c2. And if you think about it, this makes sense. If lines are parallel, then their direction ratios will be proportional. If the direction ratios of the first line are 1, 2, and 3, and the second line are 2, 4, and 6, then they're definitely parallel. So now we have conditions for perpendicular and parallel lines. Let's apply them. Let's solve a few problems. Here are two of them. Show that the line through points this and this is perpendicular to the line through the points this and this. And the second one says, show that the line through the points this and this is parallel to the line through the points this and this. Now pause the video, try this out. Okay. So our first job is to get the direction ratios of these lines. So direction ratios of the first line are, if we subtract 3 minus 1, that's 2, 4 minus 1, that's 5, minus 2, that's minus 4. So these are direction ratios of line 1, which passes through these 2 points. Similarly, direction ratios of line 2, that's 3 minus 0, that's 3, 5 minus 3, that's 2, and 6 minus 2, that's 4. Now let's see if they're perpendicular or parallel. We have to show that they're perpendicular. So let's multiply them. 2 times 3 is 6, 5 times 2 is 10, minus 4 times 4 is minus 16. So a1 a2 plus b1 b2 plus c1 c2, that's 6 plus 10 minus 16, that's 16 minus 16, that's equal to 0, which means cos theta is 0, which means these two lines will be perpendicular. Let's solve the next one. These two lines are perpendicular. We have to show that these two lines are parallel. So direction ratios of line 1, that's 4 minus 2, that's 2, 7 minus 3 is 4, 8 minus 4 is 4, so 2, 4, and 4. Direction ratios of line 2, that's minus 1, that's minus 2, minus 2, minus 2, that's minus 4, 1 minus 5, that's minus 4. So that's minus 2, minus 4, minus 4. And look at them. 2, 4, 4, minus 2, minus 4, minus 4. They are in proportion. One of them is the negative of the other. And if you write them down, 2 by minus 2 equals to 4 by minus 4 equals to 4 by minus 4 equals to minus 1. They are in proportion, which means the lines are parallel. Let's solve a few more. Show that the lines this and this are perpendicular to each other. And the next one, find the value of P such that this line, line 1, and this line, line 2, are perpendicular to each other. Pause the video, give this a try. Okay, let's solve the first one. The direction ratios are 7, minus 5, and 1. And here we have 1, 2, and 3. If they're perpendicular, then a1, a2 plus b1, b2 plus c1, c2 has to be 0. So 7 times 1 plus minus 5 times 2 plus 1 times 3. This has to be 0. So 7 minus 10 plus 3, that's 10 minus 10, that's equal to 0, which means yes, these two lines are in fact perpendicular. And for this last one, we're given that the lines are perpendicular, we have to find the value of P. And we have to be a little careful here. In Cartesian form, we write the equation as x minus x1, y minus y1, and z minus z1. The coefficients of x, y, and z are 1. Here that's not the case. So we'll have to clean them up. So let's do that. The lines are x minus 1 by minus 3, you multiply numerator and denominator by minus 1 because you want to make the coefficient of x as 1. So x minus 1 by minus 3 equals to, and for coefficient of y to be 1, you have to divide this by 7. So you divide numerator and denominator by 7. You get y minus 2 divided by 2p by 7. And here we have z minus 3 by 2. That's fine. That works because coefficient of z is 1. So this is the equation of line 1. Let's look at the next one. 7 minus 7x. So we divide this by minus 7. We'll get x minus 1 divided by minus 3p by 7. This is fine. Y minus 5 by 1. This is not fine. 6 minus z by 5. So let's multiply by minus 1. We get z minus 6 by minus 5. So now we have the equations. Let's look at the direction ratios. We have minus 3, 2p by 7 and 2. Here we have minus 3p by 7, 1 and minus 5. Now if these two are perpendicular, then a1a2 plus b1b2 plus c1c2 has to be 0. So let's multiply and get an equation in P. The lines are perpendicular, so this has to be true, which means minus 3 times minus 3p by 7 plus 1 times 2p by 7 plus 2 times minus 5, that's 0. So let's simplify. This is 3 times 3, 9, 9p by 7 plus 2p by 7. 9 plus 2 is 11p by 7. This is 2 times minus 5 is minus 10. This goes to this side, that's equal to 10. So this makes p equals to 10 times 7, 70 divided by 11, that's 70 by 11. So the value of p that makes these two lines perpendicular, that's 70 by 11.